So I think we can maybe start with the introduction. Thanks everyone for joining today to this new seminar from the Cambridge Ellis unit. First of all, I would like to thank the sponsors of the unit for the support that they provide. Thanks a lot. And then today we have as an invited speaker Simon Olsson. He's a professor of artificial intelligence at Chalmers in Sweden. He did his PhD in statistical bioinformatics with applications in structural biology at SCARP. And in 2014, he did a postdoc at the IRB in Bellinzona and ETH Zurich, where he was working on developing methods for combining experimental biophysical data with molecular simulations. In 2016, he was working as a postdoc with Frank Noé in Berlin. He was awarded prestigious postdoctoral fellowships for this. And then since 2020, he's professor at Chalmers. Yeah, today he's going to talk about generative models as efficient surrogates for molecular dynamic simulations. I'm going to stop sharing my slides, and Simon, you can start the presentation.
Yes, thanks, Miguel, for the kind invitation and introduction. Can you see my screen? Okay.
Yeah, we can see it.
Great. Okay, so yeah, thanks a lot for the introduction and for the invitation. So I have a quite mixed background, as you heard from my introduction, and I'll be talking about some of the work that we've been doing in my lab over the past few years since I joined Chalmers, and also a little bit of the work I did coming into my independent position. So first, I'll start by introducing the people who've been doing the work, which is my group. So it is a relatively recent photo of my group in a sunny day in Sweden, which is maybe considered a rare event. And there's also other collaborators that I will not talk directly about the work with these people, but they are also, of course, instrumental to many of the activities that we have in the group. Likewise, I'd like to thank the funders for providing the necessary financial means by which that enable what we do in the group. Okay, so what do we do in the group? So we have two main focuses, and the way that I usually describe this is that we try to merge machine learning and statistical physics to devise, first of all, general purpose molecular dynamic surrogates and do closed loop molecular design in silico. So the way that we phrase this problem of devising molecular dynamic surrogates is by replacing difficult to sample processes, statistical distributions by easy to sample surrogates, for instance, normalizing flow or diffusion models. And we've had a number of papers in this area in recent years. And another area that we're interested in that I will not be talking about today is the process of molecular inverse design. This is in particular in collaboration with AstraZeneca and collaborators at the MDC in Berlin on both small molecule and vaccine design. Okay, so molecular dynamics, why do we care about molecular dynamics? Ultimately, what we're interested in is describing observables of molecules, which are essentially functions of state. So if we imagine for a moment that we have a potential energy model that is describing the rotation around this methyl group here, and the corresponding potential energy is given by this function here is just a one-dimensional potential over the configurational space omega, and the rotation angle is encoded here by x. Then we can characterize this state by a macroscopic variable, which is, for instance, temperature or pressure or chemical potential or other things. And once we decide what macroscopic parameters to fix, we get an ensemble, for instance, the canonical ensemble of Boltzmann distribution, which gives us a statistical distribution, which we know up to a normalizing constant, typically just by specifying this potential energy model U of x. And the nice thing is that we can directly compute these observables O of F by simply, in quotation marks, integrating over the entire configurational space with respect to a microscopic forward model of the observable. So an observable could, for instance, be a binding free energy of a drug to a protein. It could be the solvation free energy of a small molecule going from vacuum to solution, or partition coefficient of a drug going from a watery solution into a membrane or into a organic solvent. Another type of observable, so these types of observables that I've been describing here, they're all stationary observables, so they only depend on the equilibrium distribution of the system. But there's also a different class of observables that are characterized by the dynamics of the system when a system is evolving according to, for instance, a stochastic differential equation, such as the overdamped Langevin equation, as I've written down here. Then there will be a transition density that is defined, where we define that specifies a probability distribution over our configurational space, that given where we start in a particular state x0, there will be a distribution of states that will have different probabilities at some time t into the future from that time index 0, where we are starting in the yellow state. And those observables, they are also characterized by expectation values, but here in particular time correlations, where we are looking at sampling initial conditions according to the Boltzmann distribution Px0 here. And we are then sampling this conditional transition density and marginalizing over all start and end points and evaluating the observable for these forward models G and F at the start and end points. And this gives rise to the dynamic observables, for instance, binding rates. But the issue with these evaluating these observables, of course, is that we have these integrals that are intractable in high dimensions. So in one-dimensional systems, like the ones that I've looked at here, we can evaluate them analytically, but in general, we cannot do these integrations. So what we do instead is somehow to come up with some sampling schemes, and then we use Monte Carlo estimators of these integrals. So for in the case of equilibrium observations, it's simply if we sample IID from the Boltzmann distribution, we can simply compute simple averages. If we are computing dynamic observables, we first need to sample initial conditions, then propagate them with the conditional transition density, and then we can compute start and end point correlations. So in practice, what we do, or the traditional workhorse, has been to simply solve a stochastic differential equation by doing a discrete time discretization, and for instance, using a forward Euler or some other integration scheme. And this gives rise to an expression of how we sample displacements of an initial condition, given an initial condition. And so this takes the shape of a normal distribution, but the problem is that since we need this integration to be stable, we need to choose this time step tau to be a tiny value. And so if we are looking at our one-dimensional case from before, is that essentially our transition density is only sampling in this orange area here, whereas if we want to sample to global equilibrium, we can imagine that the sampling across these high free energy barrier will correspond to rare events, and we will necessarily have a hard time drawing independent samples. A different way of visualizing or realizing this is by looking at the time correlation of samples by comparing molecular dynamic sampling, where we see that there's a high correlation for long time horizons between subsequent samples compared to IID sampling, where we have instantaneous decorrelation of our samples. And so the interesting thing here is that there's actually some physically interesting information in this decorrelation plot here, where we can see that the global mixing time that is related to the leading eigenvalue of a Markov operator that is associated with this stochastic differential equation. We'll return to this a little bit, but the main takeaway here is that if we use traditional sort of mechanistic approaches to draw samples from the Boltzmann distribution, or to generate samples that we want to use to compute observables with, we will have a biased estimator because our samples are correlated. And so there are basically two main limitations with these empty simulations. One thing is the thing that I just pointed out, is that we need to do a large number of steps to reach the timescales of interest, where we have global mixing and we're drawing independent sampling. And the other problem is that each evaluation, so taking one step, is in general polynomial in the number of particles that we are studying. So we have expensive steps. And so the opportunities that we've seen in molecular dynamics is that we can either build surrogates, so we approximate these difficult to sample distributions with easy to sample approximations. We do model reduction, so we do some sort of coarse graining, or we learn some collective variables where that makes it's easier to sample or reduce the problem to something that is more easy to directly tackle. Or we can make accurate force field models faster by building machine learning for surrogates that have a lower complexity compared to the baseline or the reference model that we're looking at. So this has been one of the extremely successful areas of machine learning for molecules, and it has now, I think, become more or less the new state of the art and reference way of doing molecular dynamic simulations, at least at the ab initio level. So how can we build surrogates of molecular dynamics? A simple idea is simply to, if we, for instance, go into a database and we find a number of experimental structures here shown with pink, we initialize short simulations from each of these states. We do a discretization, and then we count the transitions that the stochastic sampling transitions that we do between these different segments in this phase space that we have, configurational space that we have done. So by running a large number of these simulations, collecting all the transition statistics, we can simply build a Markov model based on the transition counts. And then each of these elements in this transition matrix corresponds to a conditional transition probability, and this is broadly what is known as Markov state models. So there's usually a little bit more involved than doing this in practice, but this is the gist of the idea. So the wonderful thing about Markov state models is that that we can do a spectral decomposition of this transition probability matrix, and we can use this spectral decomposition to directly compute these complicated integrals as simple linear algebra operations, so inner products or sums of inner products. So our complicated integrals reduces to relatively simple linear algebra. So the problem with one of the problems with Markov state models that we often see is that when we try to do this exercise where we initialize simulations in different metastable phases, is that we never see transitions between the major metastable basins. So we don't have any statistics of what's happening over this barrier, for instance. And so the corresponding problem is that when we collect our transition counts here in transition matrix, we have a block diagonal matrix where we don't have any connections. And this leads to, when we are doing a naive maximum likelihood estimator, that we get a disconnected Markov state model. So one thing that one of my graduate students looked into is how can we use experimental data to then augment this likelihood function such that that we can recover a transition between these two metastable phases. And we can simply do this by enforcing that the reconstructed transition probability matrix reproduces some correlation functions that we've measured in experiments. And this gives then rise to an estimator that then recovers a connected Markov state model, and we can then say something about the underlying the process that is going on here, even if we haven't seen a transition in simulations. And so we use this to study this model system BPTI, where it's dominated by some rotameric transitions that is happening in these disulfide bridges. And these four states are the major configurational states that characterize the system. And we saw that if we systematically remove transitions between the first two and the last two states, that each constitute to a major metastable basin, we could recover the accurate transition rates between these states by matching to experimental data. So here, this is NMR's relaxation dispersion experiments, where we see that if there's exchange happening on a time scale that is proportional to the value on the x-axis, we will see a drop in the relaxation rate. And we can also see that in the cases where we haven't seen where we haven't seen the rate, so here we see the different eigenvalues, or a value that is related to the eigenvalues, which is related to the timescales of the system, that we can recover those values even if we haven't seen the process in the simulation input simulation data. And so we extended this to a practical case where we didn't have a ground truth, but where we had extensive experimental data from our collaborators at the Technical University in Munich. This was led by postdoc Mark Bostock at TU Munich, who's now actually in AstraZeneca in Cambridge, and my graduate student, Chris Kohlhoff. And so here we were interested in understanding the pre-recognition dynamics of this anticalin binding protein. And what we did here is that we conducted, there was regular molecular dynamics simulations happening of the unbound and bound states. And we didn't see any transitions between them, but using the experimental data, we could recover these transitions and match the experimental data very nicely. But the most interesting part of this was that then we discovered a very persistent contact in one of the states that was not present in the other state. And then when our experimental collaborators went back into their data, they could actually identify this contact from their experimental data. So here was a way that our modeling didn't only like fit the data, but it could also inform some new ideas for enhancing the data analysis and further validate what our model came up with. Okay, so one of the big problems with Markov state models is that we have to go through this process of discretizing the configurational space. And so one of the ideas is, of course, that can we avoid to do discretization and then use some more complicated model than a simple Markov model to build a surrogate. And so the typical idea is that we define some prior distribution in a latent space, and then we learn a map from this latent space to a configurational space that is difficult to sample from. This could, for instance, be a Boltzmann distribution. And so in order for this to be a useful endeavor, we need to put some constraints on this function f. And we need to be able to, that basically allows us to be able to compute the probability of the sample. And some examples of this is normalizing flows, or that includes diffusion models, if we interpret them as probability flow ODEs, and autoregressive models. So if we just a brief primer on this, if you're not familiar with this, if you're very familiar with this, I apologize, but the basic idea of probability flow generative models is that we essentially parameterize a model, this f, as the solution to an initial value problem of an ODE that is defined by an ODE, where the initial conditions are drawn from a simple distribution here, p sets, or for instance, a Gaussian distribution or uniform distribution, depending on your domain. And then the idea is that we parameterize this velocity field in such a way that the push forward density closely matches our Boltzmann distribution or data distribution. So an example of this would be like mapping, for instance, from a uniform distribution to a bimodal distribution on a circle, or also other things that we've seen is, for instance, generating images from noise with these text conditioned image generation models such as DALI 2 and stable diffusion and so on. And so what Boltzmann generators is essentially one specific instantiation of this idea, where the original initial implementation of these were implemented with a number of coupling flows, so not a continuous normalizing flow, but discrete flows where you have multiple invertible transformations that allow us to both compute a sample efficiently and then also evaluate probabilities. And since we can evaluate the probabilities, we can also reweigh from the biased modeling distribution into the unbiased Boltzmann distribution asymptotically. So the issues, of course, as many of you probably in the audience are familiar with Boltzmann generators, is that in their current state, they have limited generalization. They are relatively brittle in training, and they are very sensitive to when one does energy-based training, which is the most appealing strategy for training, then it's very unforgiving to very small errors, and this leads to low effective sample sizes. So some examples from some recent literature, I know that there's a lot of other work, for instance, from Miguel's group that has made significant strides to improve these effective sample sizes, but some recent examples of generalizable models that really show here that the acceptance probabilities, they are sub 1%, and more recent examples, they reach up to 10% sample efficiencies for these types of models. So it's really remains a relatively big issue to actually make these models useful, because every time one draws a sample, there's a computational cost associated with it, and if we have to discard 90% on 99% of all our samples, the cost per sample, independent sample, grows up quite dramatically, as is hopefully obvious. So what can we do about generalization? And here, geometric deep learning has been, of course, an important aspect, an important player, and one can use the ideas that were introduced amongst others, but for instance, by Tess Smith and Max Welling, where we define principles to define convolutions, where we make use of the molecular symmetries. And so this has been, for instance, very helpful in this field of machine learning potentials. And here we also have some locals in your audience that have been very instrumental in making this thing happen. And so basically the outcome of this is that we have these molecular potential neural networks that are basically, by using these molecular symmetries, we get physically informed parameter sharing, so to say. But the problem with this type of approach is that we still require explicit simulation. So this is what I was referring to before, is that we get a better potential energy model that is maybe way more efficient, but we still have the sequential simulation problem. But we could also build transferable Boltzmann emulators here, where we don't necessarily try to directly model the full state space of a molecule, but maybe a subspace. And this was work that was led by Juan in my group. And here the idea is essentially to split up degrees of freedom in a molecular system into things that typically undergo slow motions, and then relax the fast motions by running short explicit MD simulations on the samples after reweighting. And so the way that this was implemented was that we have the slow degrees of freedom, which we characterize by torsion angles. We learn a torsional diffusion model to represent the Boltzmann distribution in this reduced space. We generate samples and run short simulations on this. So the process is as follows. We have our Boltzmann emulator model. We sample initial conditions. We do reduced energy reweighting, where we basically define a reduced potential energy that is only spanning the space of our Boltzmann emulator. So for instance, the torsional terms and non-bonded terms for the potential energy. And then we do reweighting based on this. And then we run short parallel MD simulations to recover unbiased equilibrium statistics. And so we use this, for instance, to do calculations of solvation-free energies in implicit solvent, and we compared this against a replica exchange baseline, and we saw that compared to classic MD simulations with a comparable MD simulation budget, we got a factor of 5 smaller errors on the absolute errors on the predictions. But this was, of course, a nice example. So this is all, I have to stress that this is all test case prediction. So this is all these, each of these dots here corresponds to a different molecule that is a test from the test set, and so not seen during training of our original model. this was, of course, a very nice illustration of the idea of that we can generalize these types of models if we make some compromises on the scope of them.
Sorry,
so
one quick
question
on this. Do you have any results on the time of compared to the replica exchange?
Yes,
like,
so,
I mean, in terms
here these two the simulation budgets here were from the SMAMD and MD. They were calibrated the compute times. The replica exchange simulations were substantially longer, but we're not sure whether we needed them to be that long to get these results. So that we haven't controlled.
Okay,
but it's a good question. Okay, so the next question is then, okay, so we've now been concerned with equilibrium properties, so solvation-free energies, but can we also get some insight into the dynamics or the time correlation statistics?
Sorry, could I ask a question about the previous slide with the salvation results?
Yes, absolutely.
So those absolute errors, in what quantity is that? I don't know if you said that and I missed it. Apologies.
That's in KBT.
So usually KBT? So,
yeah.
Sure, but like I guess the Boltzmann constant is for kilojoules or for kilocalories, or electron volts.
Well, it's in it, so so they are unitless. We have done a temperature, so the units of the absolute mean absolute error are unitless because they are that's what we call KBT because it's a classical estimate. But it's so if it's equal to 1, then we have an error which is on the order of KBT. So it's a fraction of KBT that's the unit.
Okay, and I guess a second question is on which data set of molecules did you compute these hydrations on?
So these are small molecules that are a subset of QM9, but we ran explicit MD simulations ourselves. So that's the scope of these.
And you put them in a water box for the purpose of computing the hydration, or you use an implicit solvent?
This is implicit solvent.
Okay, gotcha. Okay, yeah, thank you so much.
Sure. Okay, so any further questions to this part? Otherwise, I'll move on to the time correlation. So here in this area, we are then moving from simply sampling equilibrium statistics to sample conditioned on some initial condition, into some time horizon nt into the future, where t is some unit of time with and n is some integer value. And the idea is here, then we sample essentially the transition densities with different time horizons, where we know that if we go to very large time horizons, we'll be sampling Boltzmann again. So we'll be sampling from the equilibrium distribution, since we have a gradual relaxation to the equilibrium. And this is what we refer to as implicit transfer operators. And the reason why we refer to it as implicit transfer operators is because the model that we can interpret the transition density that we are learning as a projection of the transfer operator onto two states. So the transfer operator it's a Markov operator that acts on probability densities and transport them forward in time. And so it depends on the equilibrium density, so the target distribution that it converges to, the initial density that we're using. So that could, for instance, be a Dirac delta around an initial condition, and then a transition density that is specified by our stochastic differential equation that is giving rise to the dynamics that we're observing. And so by writing this on the spectral form and doing some trickery that we are detailing in our paper, then we can write the transition density here as comprised as an infinite sum over eigenvalues and projections of our state onto the eigenfunctions, corresponding eigenfunctions of this operator. So in practice, we don't use this for training the model in the first instance, but it gives us some intuition about how we can, for instance, train the models. So since we know that there's one eigenvalue here that has the value of 1, and all of the other ones have absolute values that are smaller than 1, then we know that for when n goes to infinity, then there will just be a single term left where there's a 1 times the projection onto the equilibrium distribution times a constant function. And this gives us, so the reason why this is interesting is that we can vary this n during training, and then when we're estimating a transition density, we can see different linear combinations of these eigenfunctions and eigenvalues, or the model will see different contributions of these things during training, and then hopefully get a better idea of how to disentangle the different contributions. This is all speculative. We don't have a clear proof for this yet, but in practice, what we see is that it works quite well. And so the second leading eigenfunction here is this leading eigenvalue that I was talking about before here, that tells us when we have reached when we relax to the global equilibrium. So just to put this into context of what I discussed before. Great. So when we deploy this in practice on a simple system like alanine dipeptide, we implement such an ETA model using a simple denoising diffusion probabilistic model with a SE3 equivariant score model, and we train it on basically by sampling initial conditions from random points in an MD simulation, and then taking n steps into the future and predicting that state conditioned on the initial condition and the time horizon. And so when we do this, we can do exercises such as this, that we can sample one shot at large time horizons. For instance, we start here at the red dot, which corresponds to 2 configurations of these 2 torsion angles, and we sample using our model in a single step fashion to any point here that correspond to a time correlated jump of 8 picoseconds. If we then compare this direct sampling on these marginal plots, which are basically projections of this 2D histogram onto the X and Y axes, if we compare the direct sampling, so one-step sampling with iterative sampling, we see that we are in distribution matching each other, which suggests that our model is Chapman-Kolmogorov self-consistent, which means that we can break down, since we know that we have a Markovian dynamics, we hope that this is the case, but we see that it indeed actually learns this. So of course there are slight discrepancies here, but we are not incredibly concerned about this because these variations are fairly small. That's the first thing you can see here. This is in the log scale, so it's really, really in the tails of the distribution we are off. And second of all, since we are training a model that has been simulated representing only the solute, but we have the original data was simulated with explicit solvent. We're effectively doing a coarse graining, which should have an impact on the actual, whether this effective operator that we are learning is Markovian. It should actually not be Markovian, but we see that it's approximately Markovian. All right, so we can extend this to larger systems. So here we are coarse graining even further. So we are representing these small fast folders with C alpha only representations. And we can do long stable rollouts with 5 nanosecond time steps, where the original time steps of the simulations were 2 femtoseconds. And we can see that if we follow along here, these are some reaction coordinates that indicate folding and unfolding. Where you see a blip, there's a folding event happening, and otherwise it's sitting in the unfolding event happening, otherwise it's sitting in the folded state. And we can compare the original MD data and a random trajectory generated with 5 nanosecond time steps. We can see that the statistics look extremely similar. And we also see that the folding trajectory looks quite similar to the training data. We can repeat this exercise and compute these observables that I was talking about in the beginning. For instance, free energies of folding, the average time of folding and unfolding, and compare these against corresponding values estimated from the original MD data. and we see we accurately capture this. So this is of course an exercise where we are overfitting the training data, and we are simply seeing whether we can reproduce the statistics that we've extracted from this. We see that we can actually faithfully reproduce the highly this statistical distribution highly accurately, and even the tails of the distribution, since these rates here, they really depend on getting the tails very right. Otherwise, these estimates will be completely off. All right, so an immediate extension of this idea is to actually make use of the spectral decomposition of the transfer operator. And so this is what we did here, is essentially to use Boltzmann generator priors for, so introduce Boltzmann generators as priors for implicit transfer operators. Because the issue with E2 models, so these implicit transfer operators, is that we require long, unbiased, empty simulations. And these E2 models, they only converge to a Boltzmann generator for long time lags. So we can use this spectral decomposition that we see here, factor out the equilibrium part, so the one that corresponds to eigenvalue 1 from the sum, and we absorb this into one score model, and then all the things that relax with time we absorb into a separate score model, where we have now introduced an eigenvalue, an artificial eigenvalue here, lambda hat n, that basically defines the time scale relaxation, the global relaxation time scale of this part here, which corresponds to this whole sum. So it's basically a redefinition of the units of the time scale. So this we can parameterize with the Boltzmann generator, and then simply fit the delta here by using exactly the same training objective that we had in the implicit transfer operator. An illustration of this approach is essentially this, that we can use now, for instance, data that is obtained with biased MD simulations, for instance, replica exchange or other approaches, to train a Boltzmann generator. And then we can collect a lot of off equilibrium, so not simulations that are not globally mixing from samples drawn from this Boltzmann generator. And then we can reconstruct the other spectral components by pooling this data together and training a joint objective. Great. So the nice thing about this, yeah, go ahead.
Can I ask two questions?
Sure.
First, let's say if I understand this correctly, you train a conditional diffusion model based on the current state and the time step you want to predict.
Mm-hmm.
And do you train this? When you draw sample, do you draw it following the PFODE, which gives like solving the PFODE and then return the density, and you can reweight it, or you just draw sample following the diffusion style? So it's a sample with density or sample itself.
So we did both sampling with the SDE and the ODE formulation. The ODE in principle, as you say, allows us to evaluate sample probability. So we could treat it as, for instance, a metropolis Monte Carlo move. We could do metropolized sampling, so we could get unbiased equilibrium samples, but we cannot get unbiased dynamics. So this is a bit of more of a longer discussion, because if we want to get unbiased dynamics, we need to do reweighting with respect to the path, the path in the path space, which is something that where we don't have a ground truth to calibrate against. So here we are So the point of let's say of illustrating this is essentially that even if we have a modeling error, the errors of our predictions are so small that that it doesn't seem like it's worthwhile to go to the trouble of doing reweighting.
Okay, I see.
So I hope that this answers your question.
Yeah, it makes sense. And for the second question, I think this slide, can you show these two equations?
This one.
Yeah, there's two. Yeah. So if I understand this correctly, the first equation, the mu is the stationary distribution.
Right.
Is that true?
Yes.
Okay. So the stationary distribution plus some term is the transition density, the stationary density, and then you parameterize your predictor as the summation of one diffusion model for the stationary distribution and one diffusion model for the prediction. And how does this make sense? Because if the score is the log of the density, and take gradient, but the summation happens in the density, and now you parameterize the score by the summation.
Yes.
Does it really make sense?
It does. It does make sense. The details are in our preprint. I mean,
Okay.
we make one assumption about about this term here, the score of the dynamic part. But we go through the derivation in the paper. So if you're interested,
Okay.
I suggest you check it out. I mean,
okay, thank you.
Yeah.
No.
But yeah, it's a good point. It's not obvious that the score and the probabilities, the conditional probabilities, they would necessarily follow the same expression. But we make some assumption about this thing. It's not exactly the same thing as up here. This contains some additional terms that we discuss further. This is also why the parameterization of the score model includes some more terms than what you see up here.
Okay.
If you had a product for the probability, it would work out more easily, right?
Yeah. But it's
exactly,
summation.
Yeah. Exactly, yeah. But yeah, if you're interested in this, the details are in the preprint.
Okay.
Okay.
All right. Thank you.
Sure. Okay, and so the nice thing about this is that intuitively it should improve data efficiency, but we actually see that it actually does this. So it doesn't only it's not only something that we expect, because we have to parameterize we have to learn less things, because part of the model is fixed during training. We also see this. So first of all, for a simple one-dimensional potential, the Prince potential, we see that this is what I'm showing here on the y-axis is the absolute difference in correlation in the short, medium, and long-term dynamics. So you can see this as a time correlation function that is binned into different regions. And what we are comparing here is the error, the absolute error in the prediction of this correlation function. So you can see this is an error of how well we are capturing dynamics at different time scales. So of course, lower is better. And what we see when we are training an ETO model is that we need to collect more data here. So the number of trajectories is larger. All the trajectories have the same length. So we need to collect more data in order to reach the same error for the long-term dynamics compared to Bopito. So the Bopito approach allows us to capture the long timescale dynamics with a fraction of the data for these simple systems. And the same thing is the case for alanine dipeptide, where we did a similar experiment here. We see that for ETO, the long timescale dynamics takes quite a long time to reach the levels. So a factor of 5 or 6 larger number of trajectories that we need to collect in order to reach the error levels that are comparable with 5 trajectories in the Bopito approach. Of course, there's more information that goes into training this original model, this Bopito model, but we argue that collecting that data is more straightforward than collecting a lot of unbiased MD data. So another thing that is interesting that we can do with this model is do time scale extrapolation. And this is the way that we've parameterized the score model, is that we can essentially tune this artificial timescale or eigenvalue that we have introduced to match experimental data if that's available. And so, for instance, in the case here where we have a Bopito model that has, of course, knows about the equilibrium distribution, and then we have an unbiased ETO model that is trained on globally equilibrated simulation data, and one that is biased that has not seen this middle region at all. So these states here from 0 to around 2.5 on the phi torsion angle has not been seen during training at all for the biased ETO model, and has not been seen for the Bopito model, but it does know about the equilibrium distribution. Then we can do interpolation. So once we reach across a certain threshold, we see that the Bopito model is actually predicting that there's a mode, or there's a transition to a mode that it hasn't seen. And whereas the ETO model, when we go to longer and longer timescales, it does not predict the existence of this state. So this state never appears in the ETO baseline. So this is a way where we can say, okay, even if we don't see transitions, we can make use of this interpolation trick to sample or to get a first estimate of the transition density into the transition probability into states we haven't seen in unbiased simulations. And we can calibrate this against experimental values. So for instance, here we are showing a correlation function along this phi distribution. So if we've seen this, for instance, in an experimental setup, we could match our Peter model here to match the MD data directly by matching the observed values at 3 points, and then reproduce nicely the reference MD simulation. Whereas if we have a biased, so the biased MD here, if we train an E2 model on this, we will never be able to overcome the bias and never be able to see this long time scale dip. So this is how we estimate this, or how we can estimate this lambda in practice, even if we haven't seen a transition between the slowest process in the system. Great. So another thing that we have been looking at a little bit, and we have just submitted a preprint today about, is how we can generalize across thermodynamic states. So here the idea is that so far we've been thinking about simple or Boltzmann distributions where we fix the thermodynamic parameters, where we are not interested in changing temperature or pressure or something like this. But what two of my master students, Selma and Wei Long, they set out to do was to say, okay, can we parameterize a change in a probability in a Boltzmann distribution that is characterized by two different thermodynamic states as the solution to an ordinary differential equation. So they're basically defining a flow that interpolates between different Boltzmann distributions. And so the idea with this is that we could have in principle simulate, for instance, at high temperature, and then to transform our statistics into a low temperature ensemble without having to do explicit simulations at low temperatures, and thereby avoid repeated simulations. So a brief outline of how this setup works is that we have two different thermodynamic states, and we can learn to map between these either through a latent space, so for instance, using two Boltzmann generators, or directly from state A and state B. And so we'll be comparing these two that we refer to ambient TI, which is from directly in the configurational space, and latent TI, where we go through a common reference state, so a Gaussian distribution in a latent space. And so we apply this to some relative. Yeah, go ahead.
So sorry, can I ask a question for the last slide? So you formalize this changing in the temperature by a neural ODE, right? And how you train this thing? You observe data, for example, you run Ellis and on different temperature and get a chain of samples, and you feed neurally to this reactor, or you just observe two ends. I don't know, you observe the density, or you observe the sample, or you observe the sample along the whole trajectory.
So this is based on flow matching between samples from the two different distributions.
So
the idea is that we have a set of temperature pairs, beta 1 and beta 2, so statistics seen in those two at training time, and then we do something else at test time.
Okay.
So
you do something else, right?
When we are testing, we are in either interpolating or extrapolating to a temperature that we haven't seen. That's the setup.
Okay, so it's based on the assumption. Is it based on the assumption that some middle point in the flow matching, for example, time 0 to 1, for example, time 0.5 is corresponding to some temperature? Is based on this assumption? No,
we don't assume that we have a meaningful intermediate distribution.
Okay, but
so, because that would require us to basically make sure that our density is always thermodynamically. That was the original intention. Doing so, basically we would just collect statistics at two temperatures and then interpolate the entire range. The issue with doing this is that it's very difficult to guarantee, very difficult to sample, to guarantee that your intermediate samples when you're doing interpolation is actually following and
following the temperature you want. Yeah.
Exactly. Yeah. So that's very difficult to guarantee in general. So I've discussed this a little bit with Francesco Giovanni about using the ideas from metric flow matching to overcome this, but it's not something that we have discussed in detail so far.
Okay.
I think it's something that one can look at in the future for sure.
What's the title for this work? Because is there a paper in like preprint version or somewhere?
I've just submitted it today. If you send me your email,
okay.
I can send you. I've just submitted it today. It's called thermodynamic interpolants.
Okay. Thank you.
Great. Okay, and so one thing that we can use this for is to compute free energies. We here get relatively modest effective sample sizes with these different strategies here, but we can compute free energies upon temperature change, where the reference temperature is given here in the dashed line, and the target temperature, which is at this time not seen. We see that they follow each other quite nicely. The three different estimators that we have that we describe in our manuscript. We also see that the marginal distribution over the major torsion angle in this small molecule, they match quite nicely. So when we start from our high temperature ensemble shown in black and we map to the low temperature ensemble shown in purple, then that we see that we actually quite nicely match in the target, with the exception of this case here where we over concentrate a little bit on the mode. We can also, by making use of some developments done by our colleague Felix Nüske at the Max Planck Institute in Magdeburg, we can estimate a generator that is associated with the ensembles that we have estimated, or that we can generate. So we can compute temperature-dependent rates of the process of exchanging between two different rotameric states in this small molecule by making use of generalized extended dynamic D-mode composition, and so we can also get access to dynamics or kinetics even if we haven't if our model doesn't know anything. So of course the critical point here is to make clear that that we are assuming here that there's a specific stochastic differential equation that is the generator of the dynamics that we are estimating. And here we are assuming it's overdamped Langevin, which is very rarely the case for molecular dynamics. So in our paper, our preprint, we are also investigating how this relates to underdamped molecular dynamics, but we see that the results of this estimator are give us a lower bound on the rates, and future work we will explore the impact of actually extending this approach to the underdamped example case. Great. So we could also scale this up to slightly larger systems. So this is again relatively small system, but substantially larger. And here where we don't do any reweighting, so we just take high temperature ensembles and we just solve the ODE to generate low temperature ensembles, and then we compute the rates here again, and we compute histograms in some low dimensional representation of these molecules, and we see that we can quite nicely match the reference MD ensembles without doing reweighting, and also quite nicely match the MD rates here as a function of temperature. So it basically shows that that the model, even if the sample efficiencies are not high, it can give qualitatively quite accurate results.
One thing, so Simon, just because you told me that you had to leave early to go to the airport.
I'm realizing that that's also why I'm running a little bit now, but I'm summarizing now. So let's
okay, good.
So basically the idea here is that we have generative models, generative surrogates for molecular dynamics can predict they're robust to model reduction, so coarse graining. They can generalize outside training data, but there's some challenges that remain. Computational efficiency is also still a big problem. Going forward, we we hope to bring together more data sources to scale this up. And one of the big unanswered questions is that if we want to compute unbiased samples from our target distribution, the computation of divergences is still a big problem for neural ODE based or continuous normalizing flows. So yeah, thank you for your attention and all the questions along the way. Yeah, thanks a lot. I think you need to leave soon. I assume we won't have time for questions. We already had quite several questions during the talk. And if anyone wants to follow up, I think they are free to send you an email or so if they have any questions. Yeah, absolutely. Please, thanks again, Miguel. Please feel free to send me an email or reach out to me in any way. I'm happy to talk.
Can you put your email in the chat so we can?
I'll do that.
Good. Yeah, Simon, thanks a lot for all this amazing work and nice presentation. And yeah, hope to see you soon and safe travels. Yeah, thank you. Take care. Good. Bye. Bye-bye.